Lastly, let us consider the analysis of a discharging tank. So let us draw a tank like this and an orifice over here. So the level of water in the tank is at a height h above the orifice, and water is effusing out of the orifice. So because of the pressure, the streamlines, they will converge a certain distance beyond the orifice before whatever happens. It can fragment into, I mean, if the flow is not so steady, it can fragment into droplets and all. But there is a presence of a vena contracta at a certain distance beyond the orifice. And typically, in order for ensuring a smooth discharge, so what happens when you cannot ensure a smooth discharge? If you cannot ensure a smooth discharge, then you end up losing a lot of energy and you end up creating a lot of non-idealities. So you have to somehow ensure a smooth discharge by means of mouthpieces. Well, mouthpieces are sort of a smooth contoured objects which you will find attached to brass instruments. So if you ever look at a trumpet or a trombone or stuff like that, they usually have a mouthpiece which is to make a smooth flow of air from the mouth to the object, to the musical instrument. So mouthpiece is attached over here. So now we can apply Bernoulli theorem between any point. So let us consider this as a reference line. So any point which has a distance z1 from the orifice to the vena contracta. So thus we can write, so let me call this as 1 and let me call this as 2. So P1 plus half rho V1 square plus rho G Z1 is equal to P atmosphere. So the jet that comes out from the orifice is essentially coming out to the ambient atmosphere, and the pressure at this particular point reaches the atmospheric pressure. So this plus half rho V2 square plus rho G Z2, but we are considering the reference point to be at point number 2. So this becomes 0. So we can write this as P1 minus P atmosphere upon rho G. So this will be equal to half rho V2 square minus half rho V1 square upon rho G. And there's a rho G Z1 as well. So minus rho G Z1 upon rho G. So this cancels out. So P1 minus P atmosphere upon rho G is equal to V2 square. So now if the area of the tank, the cross section area of the tank is quite large as compared to the area of the vena contracta, then A1 V1 equal to A2 V2, which is essentially the mass conservation, ensures us that V2 is going to be quite large compared to V1. So this is true when A1 is quite large compared to it. So in this, if this is true, we can neglect the half rho V1 square in place of half rho V2 square. So this becomes V2 square upon 2G, and this becomes Z1. So using the principle of statics, we can find out the pressure at point 1. So pressure at point 1 will be because of the atmospheric pressure plus rho G. So this depth will be H minus Z1. So P1 minus P atmosphere upon rho G from this hydrostatics equation is equal to H minus Z1. So this right hand side essentially becomes h minus z1 is equal to v2 square upon 2g minus z1. So z1 cancels out and v2 becomes square root of 2gh. So this particular formula is called as Torricelli's formula. And so the key point is you have to apply Bernoulli theorem between two points which are on the same streamline. Otherwise, this is not valid. And even though we have considered a point at arbitrary height z1, the formula is independent of that through this calculation shown. Now we can find out so this is the theoretical velocity. So the actual velocity, you can use the same tricks. So we can make use of the definition that actual velocity by theoretical velocity is equal to the coefficient of velocity Cv. Therefore, the actual velocity is Cv times square root of 2gh. Moreover, we can write the flux as Cv times the area of the vena contracta times 2gh. But the area of the vena contracta can be written in terms of the area at the orifice through the contraction ratio. So the contraction ratio Cc is given as AC upon A0. So this becomes Cv Cc A0 square root of 2gh. So Q upon A0 square root of 2gh becomes Cv Cc, and this is called as the coefficient of discharge. And the coefficient of discharge, as you see over here, is the actual flow rate through the orifice divided by the theoretical flow rate through the orifice. So this is the definition of the coefficient of discharge.